In the last lesson, we learnt that when the switch is closed in this simple circuit, charge starts to flow around the circuit. That it flows from the positive to negative terminal of the battery, and that the flow of charge is called the current. That's to say, it's how much charge passes a particular point every second. In this lesson, we're going to look at the voltage. Now, the voltage is a measure of the amount of electrical energy that is transferred either to or from the charge as it flows around that circuit. Let's make a note of that. So the symbol for the voltage is V, and we can say that it's a measure of how much energy is transferred per unit charge, Q. So the unit for the voltage is, well, the unit for energy is the joule, the unit for charge is the coulomb, which is a compound unit which is commonly replaced by the volt. So we can say that the voltage is the energy transferred per unit of charge, and that this is measured in volts, which is the number of joules transferred either to or from each coulomb as it passes around the circuit. So let's just have a look at this circuit a little bit more closely. You can see we've got our coulombs passing around the circuit, and well, as each coulomb passes through the generator, in this case it's a voltaic cell, but it could be a battery or an AC generator, then energy is transferred to each coulomb. That's the job of a generator. In this case, we call that energy transferred the EMF of the generator. Okay, and the EMF is the electromotive force. And it is the electromotive force which pushes the current around the circuit. So the electromotive force basically is the voltage supplied by the generator, and that is measured in volts. So energy is supplied to the charge as it passes through the generator, but as it passes around the circuit, energy is supplied from that charge to the circuit. Now, normally in an idealized circuit diagram like this, we assume that there is no energy transferred while the charges pass around the connecting wires. So in this case, energy is only being transferred from the charge to the circuit through this resistance. Now, the voltage, or the energy transferred by each coulomb of charge, can be measured by an apparatus called the voltmeter, and these are always connected in parallel to the circuit, as you can see here, whereas the ammeters were connected in series in the circuit. So we can say that the voltmeter measures the voltage, or what is also called the electrical potential difference in the circuit. So the voltage is the same as the electrical potential difference. So in some texts you'll find this referred to voltage. In another text you'll find it referred to the electrical potential difference, EPD, or the potential difference. Now, I like to use electrical potential difference rather than potential difference because it is a difference in electrical potential as opposed to a difference in gravitational potential. So the voltage is really the electrical potential difference in the circuit. Let's attach some figures to this to try and give a little bit more meaning to what we're talking about. So let's just suppose that we've got a 12 volt cell, voltaic cell here. Okay, right, 12 volts there. What we mean is then the EMF of this cell is 12 volts. That's to say, each coulomb of charge as it goes through that cell is given 12 joules of energy. That's what we mean when we say the EMF is 12 volts. Now then, as each coulomb passes around this circuit, it will then start to transfer its energy to the circuit. And as I said before, it doesn't actually transfer any until it gets to a component in these idealized circuits. Obviously, in the real world, that's not true. They transfer energy to the cables and the connecting wires as they pass around the circuit. So here we can assume that no energy is lost until it gets to this resistor, remembering that each of these red dots here represents 1 coulomb of charge. So we can say that it's carrying 12 joules at the moment. That's carrying 12 joules. This one has 12 joules of energy. This one, etc., as it goes around the circuit. And then as it passes through the resistor, that 12 joules of energy is transferred to the resistance. So when it comes out of the resistance, it's lost all its energy. It's got 0 joules now. And then back it goes to the 0 joules. Back it goes to the generator, and as it passes through that generator, then another 12 joules is transferred to each coulomb. So we can say that the voltage across that resistance, or the electrical potential difference across that resistance, or if you like, the potential difference across that resistance, is equal to 12 volts. That's to say 12 joules per coulomb.